Yeah, so hello everyone. We have had some technical problems, but hopefully everything works fine. So let's start our webinar and open day of our new program of Master of Computer Vision. Hopefully we'll have some potential students who will join our program or who wants to join our offline program in intelligent data analysis or data mining. And our brilliant speaker, Anna Petrovich from Xperience.AI, and Grigory Serebrikov also from Xperience.AI, at several talks in our online webinars. Moreover, as far as I know, Anna had some classes in data mining program. So she, I believe that both our new master students of our program and the program of data analysis and data mining will find something interesting in her talk. So Anna, you can start. You have, I believe, 40 minutes or something like this. So you're welcome.
Yeah, thank you so much. And hi, everybody. So today, me and Grigory, we will talk about how to prepare data to solve your computer vision and deep learning problems successfully. So we will try to make this talk as practical as possible, and we will be super happy to answer your questions. So please prepare them. Okay, so why are we going to talk about the data? How do we typically create computer vision algorithms? How do we create computer vision models? So first, everything starts with the data. We have the data set on which we run the training, which is a continuous process of improving a model. And then after we train the model, we port it to the target device to make sure it works in their target conditions. For example, if we want our model to integrate our model into some manufacturing facility, we will work on integrating to the target devices, for example, NVIDIA Jetson or Intel Movidius devices that will work in this facility. So our task is basically to train the model to see the objects of real life. So in training, we will have some data to do that. And then in real life, we need to make sure that our model is capable to detect the things that we wanted to detect. So on the training, in the training process, we want to make sure that our data set is very big, is very diverse, and is really, really similar to to the data that the model will work with in the real life. Currently, we work in an environment in a time, very exciting time actually, when there is a lot of different and very cool algorithms out there. So typically, when you want to solve your problem, you do the following. You go to some site like Papers with Code that represents the state of the art in different deep learning domains. You find some paper or algorithm that looks appealing to you. You go to GitHub, download it from there. Then you retrain this algorithm for your specific data, and success, you are done. This is basically how the process looks like. There is a lot of abundance of very good algorithms out there that you can use for your problems. Now, the question is, why do we have to retrain our data, to retrain on our data? The answer is the following. So imagine we work with people detection and we want to make sure it works on our manufacturing facility, like on the image on the right. Now, most of the people detectors that you can find out there are trained on MS COCO dataset, Microsoft COCO dataset. An example from this dataset, actually a random example I selected for this slide, is on the left. Now, deep learning is absolutely fantastic because of its ability to generalize to new types of data. But it's not, absolutely powerful like in generalizing to new domains of the data. What does it mean? It means that if it's trained to recognize people like the one on the left, it probably won't be able to easily recognize people on the right. And to make sure that we still can work in this new facility environment, we need to tune our algorithm on this domain, on data from this facility, or in general, on data from manufacturing facilities, to make sure that it works on this data. This is basically the reason why we cannot just, take person detection from GitHub and use it on manufacturing facilities, because it will work, but it won't be fantastic. Now, a very, very, very important notion that was formulated by Andrew Ng from Stanford, Baidu, Google Brain, and many other different companies he worked in. Now, Andrew Ng says that algorithms nowadays are easily able to solve problems that a human can solve after 1 second of looking at the image, right? So someone looks at the image for 1 second and says, there are 2 people here. It's an easy problem to solve. Then this task is solvable by the neural network. Otherwise, it probably isn't. A good example would be, so recently I was asked about a following task. Now imagine that we have a like 3D model of something, right? That is printed on 2D paper, like construction, for example, building constructions, right? So we have a schematics of the object that we want to build, and then we have the real life building, right? And we want to understand whether this building is the same as is printed on these schematics. Now, this is something that I won't be able to do in 1 second, that is for sure. And this is basically why the algorithms will be having a very hard time solving this problem for real. Now, another very, very important notion that we will need to talk about specifics of the data is the following. If you put garbage into your model, you will get a garbage model. Garbage in, garbage out. Because of that, it's really, really, really important to make sure that your data is not garbage, that is actually very, very high quality, cleaned up, and represents your real life use case. Now let's talk a bit about how do we actually get the data that we work on, right? Basically, the process typically is the following. Let's again talk about the manufacturing facilities and detecting people in them. So you have someone who works in this facility who reached out to you and asks you to implement such kind of neural network, such kind of solution for their business purposes. Now, typically you ask them to grab the data of these people from their facility, and they basically go to their facility and take photos of them. Then we use these photos, send them to the special annotation team. And this is a manual process of basically circling out every person that we see on the images, right? So there is a team of people who looks at the images and finds people there and basically puts a little box around every person. So this is how we get the data set. And then we use this data set for training. Now you can already imagine that in this process, there is a lot of variables. For example, how does this person capture the data? Is it actually similar to how we want to work it in real life? How responsible are these annotation people that we ask to, circle out every person? How do they even understand who is like a person of interest or maybe not, right? Because it's sometimes it's not that easy to understand what's going on in an image and stuff like that. So let's talk a bit about the details because they are very, very, very important here. So once again, we are here on a mission of creating the best perfect data set to solve your computer vision problem. Now, the main thing that I would like to outline in this talk, really one most important thing is that you should look at your data before training on this data. Now, this is a tedious process. We are speaking about thousands of images. Now, recently, I had a look at the data set of 20,000 images myself, and it took me about 4 to 6 hours to do that, right? Manually look through every image with its annotation to make sure that the annotation corresponds to what I want it to look like. So this is 4 to 6 hours of very, very boring work. right? You basically look at the very similar images, you get tired, you get sleepy, you don't want to do that. You actually want to do something with your brain, not only with your eyes. But essentially, this process about making sure that you don't spend months when training on this data set and not getting the result that you want. Actually, I'm not exaggerating here. You can do it for months without knowing that your data has some essential problems there. And because of that, to save time, essentially, you need to look at the data before you train on this data. Now, let me talk a bit about what do you want to find there? What types of problems you can actually find in data like that? Now, what can go wrong? First, let's talk about the data itself, not about the annotation of the data, but about the images or videos that you will work on. Now, the first and very, very, very important problem that you will find in real life that there is not enough data. Now, it's not possible to train a neural network for object detection to work on when you only have from 100 to 500 images. It doesn't work this way. Deep learning needs a lot of data to actually work well. It is a data-hungry algorithm. Now, you may want to, you actually need different amount of data based on the task that you are solving. So for classification or for detection, you may want to have from 10,000 images to actually 100,000 images. The reason for that is when you classify the image, it's only one kind of signal for the whole image, right? For example, we say, okay, it's an apple. It's not a lot of data that we get per image. And because of that, we need a lot of data. With detection of the objects, we may have several detections. We have several objects on the image, and we also classify, we find their coordinates, we regress them. But just the same way, it's not a lot of data that we get per image. And because of that, we need a lot of data to train an algorithm like that. When we talk about segmentation problems, however, segmentation is actually about providing some signal of the data per every pixel of the image, right? So for every pixel, we will say, okay, this is a background, and this pixel is a pixel of a person. And it's actually a lot of data per image, if you think about that. And because of that, you actually need less data to train segmentation task. And now the most probably data-rich type of data is 3D data. Think about MRI scans, right? Tomography scans, or LiDAR data that is used in autonomous driving scenarios. Now, we don't only have 2D RGB, photo. We also have a 3D, scan of the environment, including distance to every type of object, every object. With 3D data, you need less data. And it's also harder to get. Like, again, if we speak about tomography scans, imagine how hard it would be to take 100,000 scans of different people, right? So 3D is basically the type of domain where you need the less data to train a successful model than for other type of domains. Now, the first problem that you will encounter if you start training basically any real-life task is that your data in the training set is not like your data in the real life. A good example for that is emotion recognition task. There is a whole domain in computer vision and deep learning about recognizing emotions on humans' face. Now, there are many data sets for this problem. But in many of them, instead of taking real photos of real people, they asked some actors to show how angry they are, or sad, or surprised. And you will most probably get images like the one on the left. Now, this person is angry, but it's not like it's not really similar to angry people that you will find in real life. For example, the image on the right also represents like angry person, but it's more, like real life use case. if you train on the images on the left, like on images like the one on the left, it will most probably don't think that the image on the right represents an angry person because they look differently. So it's actually a very, very common problem when your data in your training set is not like your real life data. It may come from the fact that your real life data is hard to come by. It's hard to capture, or it was like your training data was captured in some different conditions from your real life problem. Now, one of the cases for that would be that the person you asked to make photos of people in a manufacturing site. This person was, just going around with their iPhone taking photos. And in fact, they want to work on some mounted camera on the ceiling, like they would on the image on the right. Now, this is a big problem because if we tune on the images like the one on the left, we won't be able to recognize people on the right. Moreover, if you see people on the right are really hard to detect because they have a special outfit for manufacturing, right? We also need to take this into the account when capturing the data set. So a perfect way to do that in these specific conditions would be to ask this person who is responsible for the data set capturing to take the data from their cameras instead of going around with their iPhone, right? One also very common problem that you will probably come by in real life tasks is if your data is not diverse enough. Now, diversity is a real big thing in training data sets. Imagine that you are solving a task of cat detection and you trained on the data set that you actually put an effort to make it diverse, right? You have different cats. They're represented on the image on the left. But it didn't take into account that the cats actually have many different breeds, and you can come by Sphinx cat that is represented on the right. It doesn't look like the ones on the left, so your cat detection algorithm will most certainly fail in this very case. You want to make sure that your data is as diverse as possible to account for all the different cases that you will meet in real life. This is especially important in nowadays environment, right? When we speak about people of different skin color, ethnicity, genders, and stuff like that. There is several scandals in the recent years when people who trained their data set didn't account for people of color, and they were not detected, or they were, treated not the same way as people of white skin color. So this is a really important thing to think about when working on your trained data. Now, there is a very good opportunity to collect as diverse data set as actually possible, which is actually by rendering data, right? So nowadays there is a lot of different rendering systems that allow you to render high quality data that you could use for the training. And actually there are already a lot of companies that provide such synthetic data sets for your training purposes. Now, this is applicable. This is a very good path to choose. But my point is that it's not applicable for all the problems. For example, if we're speaking about very constrained conditions, for example, we are talking about, we want to find defects in manufacturing process in some very specific type of detail that your manufacturing facility works on, some very specific type of detail. You have 3D model for this detail, you know what the defects are. You definitely can render such synthetic data to look very real and close to your target data. So you will have no problem. Another type of problems when you can do that is actually when you work on optical character recognition or text detection, especially if you have some documents to recognize, for example, passports. So this is a very rigid object that you know how it's comprised, you know the structure of it, you know everything, you know fonts, and you definitely can render high quality images with enough skill in this area. to use as your training data. But if you speak about people, I personally didn't see successful applications of synthetic rendering for people detection, because people are not rigid. People are very, very different. They have a very different, outfits, shapes, because we can move and stuff like that. So the main thing to think about when you think about whether you can apply rendering to your problem or not is the rigidness of your object. If your object is rigid, then probably you will be successful. If it's not rigid, then probably no, at least at this point of time, 2021 nowadays.
Probably someone may say that there are some generative neural networks, and recall sites like this person doesn't exist as an opposite example to this rigid, non-rigid problem. But the thing is that even with these generative networks, they can generate only the images that looks like the data set they were trained on. And here we return back to the diversity problem. You can generate for example, the back view of these people, because most of the data that these generative networks were trained on, they are portrait photos of people. Probably these people are professional models, so they look slightly different from what you will see in real life. And here is another issue with this data. So yes, I can only agree with Anna that nowadays, synthetic data generation for people, faces, or something like that is not an option for most of the cases.
I also want to add that for generative tasks, it's actually a bit of a chicken and egg problem. So to train a very good generative network that will generate a vast variety of possible objects, you need to have a very big data set to do that. And if you have a big data set of these objects, why would you need to work on the generative network? You can already take this data set and train on that. Okay, let's go forward. So now let's speak about the annotation, because there you also will find that there is a lot of caveats on how to do this correctly or incorrectly. Now, the biggest problem of the annotation that I'm sure you will come by if you start training something is inconsistent annotation. I'm speaking about some objects being annotated and some objects being not annotated at all. Another case is when the sizes of the annotation with respect to the object are constantly different. For example, for this person on the left, we can see that the box is significantly bigger than she is. For this person in the middle, we see that the object is smaller than she is. And for this person on the right, we see that it's, it intersects her leg, but doesn't. So these boxes look completely different. And it would be hard for a neural network to train on data like that. What we want to get is actually a very, very consistent annotation. Ideally, the boxes should be tight with respect to the person, which means that, like for this person on the left, for example, we want to very tightly capture the boundaries of her body, but don't have the outer space that we have also in this incorrect bounding box. It is easier for neural networks to train on tight boxes. And this is why in most public data sets, high quality data sets, you will also find that objects are tight. Another thing that you can find is data sets is that some objects that are hard to grasp will also be annotated. Here, I'm speaking about this object on the right. So definitely this is a person, but it's really hard to recognize. So it will probably not pass this under 1 second criteria that I was talking about before, right? I will need to kind of, look closer to really understand that this is a person here. Now, the best policy to treat the objects like that is to introduce another class of boxes that is called ignore boxes. This means that we don't punish neural network for detecting or not detecting this person, because it's a hard problem to solve. Rather, we wanted to focus on the people here that are really recognizable, easy to recognize, and we want to train this neural network to do it really, really well. This is our goal here. Okay, so another thing, I already touched this problem, but the boxes should be tight. I want to emphasize this once again. So it's not correct to annotate big boxes. It's not correct to annotate small boxes. The boxes should be tight with respect to the object you are interested in. Now, a very big problem, it's not actually even about the annotation, it's about the combination of data and annotation, is when it's hard to understand what's going on the image, on the whole image in this case. Now, these are examples from probably the most famous data set in the history of computer vision and deep learning, that is called ImageNet. So ImageNet was comprised of 1 million images and had 1,000 classes, and was a very important benchmark of the quality of the neural networks up until 2017, when it was decided that ImageNet is over, because now neural networks can do it just too well. So there was a person, his name is Andrei Karpathy, who actually sat down and tried to pass ImageNet test himself. So he was acting as a neural network looking at the validation set, and he tried his best to classify what he sees on the image among these 1,000 classes that he can choose from. Now, he found that in many cases, you cannot solve this problem easily in under 1 second, or you need to have some skills that we don't want our network to do just yet. For example, for this image in the center, this is a salt, but you can only understand it by reading what is written here. And general classification, if you don't want to read, if you just look at the image, it's hard to say what it is. Now, basically the same goes for other objects here. So this one is probably just incorrectly annotated, because this says that it's a ruler, but there is a lot of different stuff here that is not a ruler. For this one, well, I can probably understand that it's a crab, but it would be really, it's not an easy thing for me to do. Now here, I just don't understand what's going on and stuff like that. Now, you want to make sure that when you solve your problem, you don't have images like that in your system. I don't have images like that both in training and validation set, because it just skews the task and makes it harder for the network to train on that. And the last thing I want to talk about is augmentations. So augmentations is something that you do to your data to make it even more diverse compared to what you had in the training set. By its definition, augmentation is something that you do to the data, to the image, without changing its class. Now, it can be a lot of things, actually, if you think about that. You can rotate it, you can crop it, you can scale it, you can slightly change its colors, increase or decrease brightness and saturation. So it's a lot of random things that you can do to your data. But essentially, the main thing is it should not change the class of your data, which means that you can still see, you should still be able to see watermelon here. What does it mean? For example, if you scale too much and only leave this gray crop on the top, you won't be able to, there is no watermelon here. And it would be just incorrect to send this crop to your network and ask it to predict watermelon. It would introduce a lot of overfit or bias to the problem. Because of that, it always makes sense. Always makes sense to look at the data after the augmentations before you pass them to the training loop, right? So a good policy, to summarize, would be the following. You look at the data before the augmentations, just at your plain training set, right? Make sure that it's fine. Then you implement your augmentation pipeline, and you look at the images before they go into the training, right? So you're visualizing them. How do they look after the augmentations? And this is super important. This happens, all the time when you introduce too harsh augmentations and you cannot recognize your data anymore looking at it, which makes it really, really hard for a neural network to train on such type of data. And it's just not what you want. You want this data to be still looking like real one. Okay, so let me summarize what we were talking about here, and then we would be super happy to answer your questions about the data. So garbage in, garbage out. You want to make sure that your data is very nice, clean, and high quality before training on that. If you train on data with a lot of different noise, incomplete data, not diverse enough data, you will just not get the result that you want. Now, the most important thing that I want you to do after this talk is to look at the data, the annotation, and the augmentation before you train on that. This is tedious, this is boring, but it saves months of man work if you do that. This is basically the key difference that I see between junior and senior people, because senior people had enough experience with bad data that they know that it's better to spend 4 to 6 boring hours than several months going just in wrong direction.
Yeah, and probably this is one of the key differences between the academic data sets and real data sets, because academic data sets, they probably have much cleaner annotation compared to what you will have from your customers. And they are much more permissive to their annotations just because of their size. If you can afford to collect millions of images like an ImageNet, it's okay to have some errors in the annotation on small portion of them. But if you are limited with the time, and typically you are limited with your time when you train real production models, then you will be limited with the amount of time you can spend to collect the images, to annotate them, and so on. And that's why you want, as Anna said, very clean and concise labeling process, image collection process, and you don't want to have garbage in your data.
And the final thing that we would recommend to you to just keep calm and train models. So when you have good data set, it's just a pleasure to iterate on this data set and get better and better and better results, knowing that you go in right direction. So good luck with the data, everybody, and we'll be super happy once again to answer your questions.
Yeah, thanks. So, though I am not Alexey Kirillov, but I will be here because of our some offline and online mixture. So, thanks again for a nice presentation, and hopefully I will I will be only one who will ask you questions because of logistic and something like this. But I will gather some. I gathered some of them right now, and I will just try to formulate some of them, and probably will share some experience in these particular cases. So one of the questions from our auditory, from one guy who was interested in our program, was super practical. It was absolutely practical. So I believe you can give him some advices. For sure, it's too broad, but anyway. So the question is that he had some really practical task on detecting of some products in shops or in some, I don't know, in some markets. The problem is that these products are too small when compared to, I believe, to the resolution of the input video. So you observe the whole a lot of products, and you have to take a look at the rather large image and to detect these small products. And the problem is that he also didn't have very large labeling. I mean, some small data set like, I don't know, 10 or 15 or 20 rather different images of the same products, because for sure he can make the same photos of the same product like a video frames, but these images will be actually the same, so there will be no idea, no issue how to use them. So what is your advice in something like this? So what he should do in this particular case?
Got it. Thank you. And yeah, this is harsh. I mean, now the first question that we need to answer is whether a person looking at these high resolution, low resolution images is able to recognize the target products, right? And this is essential. So if the answer is no, then this problem is just unsolvable. You need another type of imagery or something else. I mean, approach. Now, if the answer is yes, and person can definitely say what type of product it is. Now, two things. First, you really need very tight annotation, which is especially important for small size of objects, right? Because even small, distance, even small difference in the annotation and a real life product will be very big percentage of its real size because it's small. The second thing, you need to really think about the data augmentations, because they may enlarge your data set significantly. And I can imagine a lot of augmentations that can be applied in this case. And finally, I would recommend, if we're speaking about the detection, so you will need to be very cautious about the architecture of the network to make it work with the very small types of objects. Depending on the architecture of the detection that you have, like one shot or not, you will still want to, look deeper into how you form the detection areas to account for very small boxes. Yeah.
Yeah. Okay. Thank you. Hopefully, it will help in some way to understand the complexity of the task also. So speaking about, so thanks. Let me recall another question. It's about, it's also rather typical questions from different auditors of our webinars, and right now we have also had something like this. So you know that the neural network models can be launched on large servers with tons of GPUs, or they can be run on mobile devices, on edge devices. So from your experience, what is the current trend? Something client server oriented, or something mobile oriented, or something like this? So it's what will be most popular products in computer vision, I don't know, in the next 5 years, for example? What's your opinion in this case?
So definitely the trend is to move the neural networks to the edge devices instead of using servers for them, for many different reasons, not only for cost, right? Because servers are really costly, but also for privacy reasons, because you may not want to, send your imagery data, for example, from some manufacturing facilities or from offices or from actually anywhere. You may not want to send it somewhere. You may want to keep it close to yourself to make sure there are no leaks. Now, I may be biased in that because my, preferred area is embedded neural networks, like neural networks that run on very small mobile or embedded devices. But I definitely see this trend happening in the recent years.
Yeah. Okay. Thanks. And probably the last question. So as I introduced you, you are big guys in Xperience company, and in computer vision, I don't know, in Nizhny Novgorod at least. So can you share some interesting tasks that you have recently solved in your company, or something like this? Something interesting, I mean, which goes beyond some student, or some, I don't know, some general task like classify, is it a cat or a dog or something like this. So something from the cutting edge of industry, I mean, industrial application, something difficult, something interesting in which you need some, I don't know, some experience and some knowledge and something like this. So something complex, but from industry, not from academia.
Okay, so let me give you two examples. First, like there are hard problems to solve in algorithmic sense and in engineering sense. For example, algorithmic is probably clear, but engineering is when you have a very small device to use for inference, right? I mean, really small, works on battery for like several months or even years, this small. So it's really a challenge to put some, complex neural network, high quality neural network to work on this device. Now, algorithmic problem, again, I may be biased by my preferred type of algorithmic problems at this point are 3D problems, because this data is completely different. And I believe that 3D segment of the data will be growing and growing in recent years, partially due to the, so it becomes more and more a commodity data, because in the newest, newest phones and tablets, you can already find 3D sensors. So yeah, 3D is my favorite type of data, I would say, and it gives you a very hard time, to be honest, to create a very good algorithm there. So a couple of years ago, we were able to create the state-of-the-art algorithm in 3D indoor instance segmentation. There is not a lot of as many different labs working on this problem as on 2D problems. I mean, labs in universities, and because of that, you can really change state-of-the-art in these problems. So yeah, 3D, I'm really interested in that. And another type of problems that I would probably make an example of is recently where we started working with thermal data. So this is an infrared camera that provides an image of, it basically shows the temperature of people, computers, I don't know, coffee mugs or background in the room. And the task is to detect people. So this provides a really new and challenging environment because these sensors are completely different from RGB cameras. Each sensor is unique and it has its own, type of bias and noise. And it's also, so this is really interesting. Now, the complexity of this very problem is that we also need to work on a very small device, like several months on battery power. And a combination of this, new domain of data and engineering challenge is something I personally love. And this is because this is why I would give this example here.
Yeah, okay. Thank you so much for this such encouraging techniques. And yeah, I believe multi-sensors will be the future of computer vision engineers. So yeah, I believe we are at the end of this webinar and this open day, and I would like to cordially thanks all our participants. Thank you, Anna. Thanks, Grigory. So I will switch off the camera and everything. So yeah, thanks everyone, and we'll be in touch, I believe. So thanks again. Let me stop everything. So we'll be in contact.
Thank you.
Thank you.